About half of the stars in our galaxy, and likely other galaxies as well, orbit one or more other stars. The most common multi-star system is a binary system, where two stars orbit one another. But less commonly, one can find trinary systems with 3 stars and quaternary systems with 4 stars. It's possible to have systems with 5, 6, or perhaps even up to 10 stars, but the more stars in the grouping, the more complicated the orbital dynamics and the less stable the system will be on billion-year timescales. To build realistic multi-star systems, it's important to understand how such systems form. In this video, we will start with binary systems, as they are the most common type and are key to understanding larger multi-star systems. The vast majority of binary stars form together in large molecular clouds. However, it is possible that, on rare occasion, a lone star may capture a companion while wandering the galaxy sometime after its formation. It's important that you decide how you want your binary systems to have formed, as this will determine several of its properties. Sibling binaries, those that formed together, will be approximately the same age, while this is not necessarily the case for captured binaries. They could be the same age if the capture event took place while the stars were still in their stellar nursery, or they could be very different in age if they paired up later on. Furthermore, sibling binaries will tend to orbit one another in the same orbital plane, or at least very close to it. This would be very unlikely for captured binaries, which met with random motions that result in the pair having different inclinations and orientations relative to one another. So you need to make sure that the combination of properties that you choose for your binary system is consistent with its formation method. You can't have sibling binaries that are of vastly different ages, such as a 10 million year old blue star and a 4 billion year old orange dwarf. If you want such an odd pairing of stars, they will have to be captured binaries, and you will need to define their individual orbital planes, which is going to add a lot more complexity to your project. Sibling binaries can be different spectral types, different masses, and in different stages of their evolution, but they have to be the same age. Binary systems are divided into 3 separation categories. Tight binaries orbit one another very closely, usually at less than 1 astronomical unit, but it can be a few more depending on the masses of the stars. The main defining characteristic of tight binaries is that there are no stable planetary orbits between them, though planetary orbits can exist out beyond them. More on that in the next video. On the other end of the scale, there are wide binaries, which orbit one another at enormous distances, usually beyond 100 astronomical units. Their defining characteristic is that both stars can have full planetary systems around them that are virtually unaffected by their companion star. But between these two categories are the mid-distance binaries that orbit one another at ranges greater than that of a tight binary and less than that of a wide binary. These may or may not possess stable planetary orbits between them, depending on the specific parameters of the two stars. This makes mid-distance binaries the most difficult to work with when building a fictitious planetary system, as it requires a lot of calculation to locate viable planetary orbits. Earlier, I said that binaries are the key to understanding multi-star systems. This is because multi-star systems, no matter how many stars are in them, are all organized into nested binary pairs. So if you have 3 stars, 2 of them will be in a tight or mid-distance binary pairing, while the third will orbit in a wide binary pairing with their center of mass. With 4 stars, there are 2 possible configurations. The most common is to have 2 pairs of tight or mid-distance binaries in a wide binary pairing with one another. But you can also find a single star, particularly if it's very massive, in a wide binary pairing with a compact trinary grouping like the one we just discussed. The more stars there are in the grouping, the more potential variations exist, but they'll always be in nested binary pairs. So, no matter how many stars exist in your system, you need to start by building the closest orbiting binary pair. The first parameter we need to define for that pair is their orbital separation distance, or their semi-major axis if you want to be all scientific about it, which I do. When it comes to the distances between two stars, working in meters gets ridiculous fast, so it is often better to work with astronomical units instead. So if you're building a wide binary system, your semi-major axis should be between approximately 100 and 10,000 AU. If you're building a mid-distance binary system, the separation should be between approximately 5 and 100 AU. But if you're building a tight binary system, it gets a bit trickier, as the range could be anywhere between 0.005 and a full 5 astronomical units if the stars are on the more massive side. The closer your stars orbit to one another, the higher precision you're going to need in this distance value. So if you're building a tight binary system, you'll need at least 4 digits past the decimal point, but 8 would be better. If you're building a mid-distance binary, 4 digits past the decimal point is probably sufficient. And if you're building a wide binary system, you don't have to deal with anything after the decimal point if you don't want to. I'm going to make my system a wide binary so that I have enough room for planetary systems to exist around both stars. So I'll set my star's semi-major axis value at 624.48 astronomical units. I'll add that to my SAP sheet and then convert it into meters by multiplying it by an astronomical unit. 149,597,870,700 meters. Then I'll add that result to my SAP sheet as well. The next value that we need to define for our stars is their orbital eccentricity. This is how elliptical their orbital paths are, and it's going to be a value between 0 and 1. 0 represents a perfectly circular orbit, and the closer the value gets to 1, the more squashed the orbit becomes. The majority of binary stars have orbital eccentricities between 0.4 and 0.6. And this is where I like to keep my binary systems, as it is the most common and therefore the most plausible. You can have eccentricities outside this range, but the value shouldn't be placed below 0.1 unless the two stars orbit extremely close to one another. I'm going to set my star's eccentricity to 0.4719 and record it on my SAP sheet. Once you have the semi-major axis and eccentricity, you can calculate the star's periapsis and apoapsis distances. That is, how close they will pass to one another and how far they will move apart, respectively. These values are very important to multi-star systems as they influence the stability of planetary orbits within the system. To calculate the distance at which the two stars are at their closest, we can use this equation, which relates the orbit's periapsis to the semi-major axis, in meters, multiplied by 1 minus the eccentricity. So with the calculator, we enter our star's semi-major axis times, open parentheses, 1 minus our eccentricity, and then close the parentheses. Your equation should look something like this. Press equals, and there is the periapsis of our binary system. For the star's farthest separation, we can use a similar equation, which relates the apoapsis to the semi-major axis multiplied by 1 plus the eccentricity. So just as before, I'm going to start by entering my star's semi-major axis, then multiplying, opening a parentheses, and then this time entering 1 plus the eccentricity value, and then closing the parentheses. Your equation should look something like this. Press equals, and there is the apoapsis distance of our binary system. If you are building a mid-distance binary, how close the stars come to one another in their orbit, that is, their periapsis distance, will determine how many planets can potentially orbit each star. So in that case, you may want to instead pick the periapsis distance that you want for the stars first, and then use that value to calculate the semi-major axis and apoapsis distances. You can do that using this equation, which equates the semi-major axis to the periapsis distance divided by 1 minus the eccentricity. The next parameter that we're going to define for our binary system is its standard gravitational parameter. This is a measure of the total gravitational energy of our system and is useful in calculating several other parameters, such as the orbital period and the various orbital velocities of the two stars. It is given by this equation and is equal to the gravitational constant times the sum of the two masses. So on my calculator, I'm going to enter the gravitational constant, in parentheses, 6.6743 times 10 to the power of negative 11. Then multiply and open two parentheses. I'll enter the mass of the primary star, close one parenthesis and add, open another parenthesis and enter in the mass of the secondary star. Then close both open parentheses. Your equation should look something like this. I press equals and then I'll add this value to my SAP sheet. Normally we only record 4 digits past the decimal point, but in this case it's a good idea to get the entire value. Next we'll calculate the orbital period of our two stars using this equation, which relates the square of the period to 4 pi squared times our star's semi-major axis cubed, divided by the standard gravitational parameter. So on my calculator, I'm going to start by opening a parenthesis and entering 4 pi, then raising it to the power of 2. Then I'll multiply and enter my star's semi-major axis distance and raise it to the power of 3. Then I'll close the parentheses, divide, and open a new parenthesis. Then enter my standard gravitational parameter and close the parentheses. Your equation should look something like this. Pressing equals gives us the square of our orbital period, so we need to get the square root of this value by raising it to a power of 1/2. Pressing equals again, and there is our star's orbital period in seconds. I'm going to add this number to my SAP sheet before converting it into more understandable units. This will either be days or years, depending on which is more reasonable. If your star's period is less than, say, 100 million seconds, then you would likely want to use days. In that case, you could simply divide the number of seconds in your star's period by 86,400, which is the number of seconds in a day. But if your star's period is greater than this, especially if it's in the billions like mine, then you'll want to use years. To do this, you would instead divide the number of seconds in your star's period by the number of seconds in a year. 31,557,600. When I do this, I get a value of 13,107.1 years for my star's orbital period. That covers the basics of depicting a binary system. In part 2 of this video, we will discuss adding one or more additional stars to the system and learn how to not only define the shape of the multi-star systems, but also their orientation in space. I hope you will join me for that.